Hey guys, welcome back. So I'm going to show you one more thing with music. I hope you enjoyed the patterns video I made yesterday. I know it was long with 44 minutes. I'm going to try to make today's much shorter than that, but I was showing you guys a lot of extra sources and extra videos. And honestly, the assignment for patterns is really simple. And I mean, how do you make that kind of stuff that interesting except adding all the other stuff? So anyway, one more thing I showed you with the guitar yesterday, how all the bar chords are the exact same shapes and patterns, just shifted up the frets. Same thing pretty much happens with the piano. You can actually see it pretty well as well. So if you're familiar with music, you'll notice your major and your minor scales down here, they all have the same patterns of whole steps and half steps, right? So you can change the scale by just starting by changing the note that you start on, and it just goes up the frets or up the piano or however you do it. So for our major scale, we start with our root, which would be, for a C major scale, would be C. Then we do a whole step, which would be, to the black key here would be a half step. So a whole step is actually going to be to D, so it's C, D, and another whole step, which is E, so we go past the black one here, then to E here. So our 1 to our 3 is going to be C and E, and then another whole step, which would, no, sorry, a half step, which takes us to F, and then a whole step past F sharp to G, which would be our fifth. So we have our 1, our 3, our 5, and then our other root would be the 8 over here, which is the octave, right? So we have our 1, our 3, our 5, and our 8 again, which is also our 1. So this would be a C major chord. And like I said yesterday, if you don't know how to play piano, you can play piano in the key of C by only playing the white keys. So the 4 chords of Awesome, the songs that, you know, kind of the compilation of songs that we saw yesterday, those were all playing the same simple progression, the 1, the 5, the minor 6, and then resolving to the 4, then back to the 1. So anyway, how you would play that would start up with the C chord, which is basically what we have here. Then we go up to, oops, sorry, I pushed the wrong one. Then we go up to the 5, which would be a G. Okay, so now it's G, B, D, and G again. So it's your fingers are literally exact same spacing, at least when we play in the key of C, which makes it really easy. And then we go to the minor 6, so we go up a half a step, and then we go back down to the 4, which would be the F chord, F, A, C, F. Then we go back to the C. So it starts out 1, 2, 3, 4, then to the 5, 5, 5, 5, minor 6, minor 6, minor 6, minor 6, 4, 4, 4, 4. And that's Don't Stop Believin', all the other songs that they were playing over and over and over again. And now, congratulations, you know how to play all those songs, not only on guitar, but also on piano. And your fingers literally say the same spacing over and over again. And you just shift up, and you shift up, and you shift back down. It's really simple. Maybe different inversions or different timing, but hey, now you know. Kind of really cool stuff. Patterns in math and music, all fun things. They're all kind of interrelated. So let's go back over our algebraic identity properties. So the identity property is what we add or multiply or take to the power of in order for the identity to remain the same. So a to what power is going to remain a. So, or sorry, a plus what number is going to be a itself. So it would be 0, right? Our additive identity is 0. If we add 0 to anything, it stays the same. What about our multiplicative identity? So a times 1 is going to remain a, and anything to the first power is going to remain that anything, right? So the additive identity is 0, multiplicative identity is 1, exponential identity is 1 as well. Then we have our inverse properties. So the inverse properties are how we undo certain operations like addition, multiplication, division, and exponents. Can all be undone with inverse properties. So the additive inverse, in order to get something to the identity, which is to make it go away, right? What do we add to anything in order for it to go away? Well, we would add the opposite of anything, which is the additive inverse of negative a. And so say that we start out with 4, we would add to that negative 4 in order to get it to 0. So I'll go ahead and go through these examples here. Yeah, okay, so if we want to get the x by itself, we want to undo all the stuff that's going on. X is being cubed and multiplied by 2 and then adding 4 if we follow through PEMDAS, right? So the first thing we want to get rid of is the last thing in the order of operations. So we're kind of working our way back, which is kind of interesting, by the way. Is we want to get rid of this 4. So how do we undo 4 to get it to 0, the additive identity? We subtract 4. And if I subtract 4 from one side, I got to subtract from the other side as well, because that's our subtraction property of equality. All right, so now I'm left with 2x cubed plus 0 is equal to 16. Well, when we add 0 to anything, because it's the additive identity, it goes away, right? So it's just going to be that anything. So now we have just 2x cubed is equal to 16. So the next step that we have here is at the multiplicative inverse. So the multiplicative inverse, we're trying to get something to go to the multiplicative identity, which is 1. So how do we undo A in order to get it to a 1? So we undo the multiplicative inverse by multiplying by the reciprocal, or if we're multiplying, we're dividing. It's kind of the same thing, except multiplying by the reciprocal, where we switch the numerator and denominator, we'll get rid of the multiplication and division at the same time, all in one process. So anyway, we multiply A by 1 over A, or just simply divide it by A. It's the same thing, which will get us back to 1. So how do we get rid of 2/3? We multiply it by its reciprocal, which would be 3/2, and then it would get us back to the 1. So how do we get rid of a multiplication of 2? We multiply by its reciprocal, which is 1/2, which is the same thing as dividing by 2. So we're going to end up dividing both sides by 2. Pretty simple, no big deal there. The next thing that we have when we divide both sides by 2, which is our division property of equality, is going to leave us with 1x cubed is, that should be cubed. Got to fix that. 1x cubed is equal to 8, because 2 divided by 2 is 1, because that's we undid it with the multiplicative inverse, which got it to the multiplicative identity. The reason we want that is because the multiplicative identity is going to go to it's going to, when we multiply anything by 1, it goes to it is itself, right? So that's just going to be x cubed is equal to 8. Then the last step is we want to undo a cube. Well, to do that, we have to use the inverse for that. I think I already got rid of it. Exponential inverse, and we undo things by multiplying them to their, I guess that works for me, by multiplying the power to its reciprocal. So if we're squaring something, we undo a square by taking the square root. Oh, excuse me. Lots of stuff going on here. Is it this one? Is it this one? Oh, there it is. Anyway, so 1/2 power, we do that. Half of 2 is 1, and so now it goes to the multiplicative or the exponential identity, which means it goes away. Same thing with to the third power. If we take that to the 1/3, a third of to the third power is just going to get it back to 1, which would be a cube root in other words. So over here, when we're looking at 1x cubed, how do we undo a cube? Well, we would multiply it to the 1/3 power, which is going to leave us with, right, okay, so x to the third and then the 1/3 power of both sides, which basically is going to leave us with 2, because whenever we have 2 to the third power, well, we could also put that in the calculator. I suppose I could show you that. We're going to do caret 1 divided by 3 to do the third power. I think I got rid of that message. Yeah, nice. All right, so we're going to do 8 caret, and then I'm going to use parentheses to do 1 divided by 3. And then you can close the parentheses if you want. So the 1/3 power, which will leave you with 2. Another way you could do this is 8 caret, and you have an n over d, numerator over denominator button, which is really nice, kind of a clear view thing. 1/3, and hit enter, and you'll get the exact same thing of 2, because 2 times 2 times 2 is equal to 8, right? Okay, so cube root of 8 is 2, and then we're finally done. So that's how we use inverse properties to get them to the identities, which are what you see in purple, in order to make them go away, so that we're left with, we're kind of unraveling that mess to end up with just x is equal to 2. All right, our properties of equality, I'll show that real quick. So if we want to subtract 4 from both sides, that's using a division property of equality. And then after that, let me see. Interesting. So anyway, after that, we're left with dividing both sides by 2. Okay, so that's going to be our division property of equality, because whatever you do to one side, you have to do to the other side for it to remain equal. And then after that, we're going to have x squared. So we want to undo the squared, so we're going to take the square root of both sides. So that's going to be an exponential property of equality. And then the last thing should be just the answer, I think, right? Yeah, so then we just have x is equal to 4. So the entire time those were balanced. No matter what we did, they were always balanced. When we started at the very beginning with the original equation, we knew the left expression was equal to the right expression. When we subtract 4 from both sides, they were still balanced. When I divided both sides by 2, they were still balanced. When I took the square root of both sides, they were still balanced. And then lastly, when we have x is equal to 4, we finally identified what x was equal to, which is what is equal on the other side, which is just simply 4. All right, now we have our algebraic properties. So the commutative property is going to be when we switch the order. So the commutative property of addition is if we have a plus b, that's going to be exactly the same thing as b plus a. So notice all we're doing is switching the order across the addition sign. So the addition is in between it and we switch the order. So a plus b is the same thing as b plus a. By the way, commutative property does not work for division. It does not work for subtraction either because the order matters with division and subtraction. But if we're instead of subtracting, if we add the opposite, then all of a sudden it's a commutative property of addition and it totally works. So for instance, if this was a negative b and then I put the negative b in front, so a plus a negative b, which is the same thing as a minus b, is the same thing as negative b plus a. So we can use the subtractive property, commutative property of subtraction, but it's not really. It's really the commutative property of addition when we add the opposite. All right. The other thing that we have here is the commutative property of multiplication. So notice it's the same thing. We're just switching the order of a and b and a. We actually saw this when I showed you the times table thing, and notice that it's switching it about multiplication. So the multiplication is in between the two that are being switched, the two terms. So in other words, 3 times 4 is the same thing as 4 times 3. Right? All right, then we have the associative property. So the associative property is going to be when we are regrouping. So who you associate with is like your group, okay? So if we have the parentheses that tells us we're doing a plus b first, then we add c to it. That's the same thing as doing b plus c first and then adding a to it. So we can regroup or shift our parentheses. This would be the associative property of addition because notice they're all being separated by addition. And we can also do the associative property of multiplication. So I could do the a times b first, then multiply it by c, or I can do the b plus or b times c first, then multiply it by the a. So just notice that the parentheses are shifting. And on the first one, it's shifting about addition. And on the second one, it's shifting about multiplication. So that's the associative property of addition. This one's the associative property of multiplication. So why do we have to use the commutative and associative? This is actually how we combine like terms. You just don't realize that's what you're doing. So if we have 8, 2x, and negative 6, I want to add the negative 6 or subtract it from the 8. But in order to actually do that, we have to rearrange it with the commutative and the associative properties of addition. So first step we might do would be to change the order of the 8 and the 2x. So we switch the order across the addition sign. That's commutative property of addition. And now I want to regroup. So it's understood that when we have addition and subtraction, we would just go from left to right. So in this case, it's understood that we would do the 2x plus 8 first, then we would subtract the 6 when we're done. So what we want to do is we want to reassociate that. So the first one, by the way, we said was, oh wow, that totally locked the wrong thing. Anyway, well, the first thing that we said was a commutative property of addition. And then next we want to change the parentheses from the first two to the last two. That is going to be, and again, we have to change this from minus 6 to plus a negative 6. That way it'll work. Technically it would work either way, but it's just good practice to do that. So this is going to be the associative property of addition because we're switching about addition between those two. And again, the associative property of subtraction is not a thing, so we can't do that. And then now finally we can do 8 minus 6 or 8 plus a negative 6 would be 2. So that's going to leave us with our final answer of 2x plus 2, which is just in parentheses, which is just 2x plus 2. Okay, so in order to be able to combine like terms, we actually have to rearrange things with the commutative property and then reassociate things with our grouping with the associative properties. So anyway, that's technically what's going on when you combine like terms. Of course, we don't usually show all that work, but we will on today's assignment. I know it's tedious, but it's good for you. All right, distributive property. So the distributive property, of course, you guys know this one. If we have a times b plus c, whenever you notice that these are being added and this is multiplied, we actually have to distribute the a through across both of those, across the addition. So when we do that, we're going to end up with a times b plus a times c, right? So notice that the a is now being distributed across both of them. You can also go backwards. You can factor out the a, which is called factoring or sometimes reverse distribution, but it's still technically the distributive property. The other one is the transitive property. This one's kind of fun. So if a is equal to b and b is equal to c, then we can say that a is equal to c, right? So we can kind of, it's like dominoes, right? If we have A goes to B and B goes to C, then we can skip and A will eventually go to C. So we can skip over the B's entirely and go straight from the beginning to the end, okay? So it is kind of like dominoes. So A knocks over B, B knocks over C. So we can say that A indirectly knocked over C. Or it's just a long string of equalities is another way of thinking of it. So transitive property, that one's a fun one. Then we have symmetric and reflexive. These two are probably the most commonly confused. If you got associative and commutative down, you're good. But the symmetric and reflexive are always often flipped. So the symmetric property, this whole symmetry thing, think of like a line of symmetry for like a face for this lion, which means we know that whatever's going on the right side of the face of the lion is probably going to be mirrored on the left side of the face. Oh my gosh, this is going to be terrible. Okay, actually not half bad, and I'm doing this with my digital writing. Oh, that was terrible. Let's try that again. Hey, that wasn't too terrible. Yeah, he doesn't look like he's had a stroke or anything. Got to finish off the ear though, and the hair apparently is supposed to go there. Okay, yeah. It's my Mona Lisa. It's wonderful. Anyway, so the symmetric property essentially says that if A is equal to B, then we know that B is also equal to A. So we can switch things just like we did with the commutative property. But notice now we're not switching it about addition or multiplication. We're switching it about an equal sign. That's what makes it symmetric property. So it's kind of like the commutative property of equality, but that's not what it's called. It's called the symmetric property. You can also do the same thing. Just another example, we use this all the time when we end up solving and we get 3 is equal to x. It's really the same thing we know as x is equal to 3. So that's probably how you see it most often when we're doing proofs. The other one is called the reflexive property. So what's different about the reflexive property, see if you can see it, is that we're not switching the order. We're just saying that things are equal to themselves. So anything is equal to anything. The expression x plus 4 is equal to the expression x plus 4. And if we tried solving for that, it wouldn't help because we would end up subtracting the 4 from both sides. X is equal to x, and then you subtract x from both sides, you get 0 is equal to 0. So the reflexive property, it seems kind of useless, but it's a property and we have it. I can't think of when I'd ever use it, but it's okay. It's good. I guess it's just a thing. Anyway, so symmetric property is when things are equal to another thing, we can switch the order about the equal sign. Reflexive is when it's equal to itself. So to help you remember, reflexive is like a reflection. So if we have this this baby here who's in front of a mirror, what's going to be on the other side of the reflection? It's going to be the baby, right? We call this is a very famous photo. In my class, we call this the creepy baby photo. It actually has this name, and I cannot resist. I like to draw a nice mustache on the creepy baby, and sometimes get some nice French eyebrows, and sometimes he even has a top hat. Yes, very nice. And he's been known to have a gold chain as well, because that's how he rolls, and usually a giant G for geometry on the gold chain. And sometimes we give him a ring, like a big old ring, because that's how it is. He definitely has a piercing on both sides. And what else do we do to him? Sometimes this is a little too much. All right, we'll just pretend that last part didn't happen. Oh, and anything that happens on this side, of course, has to be mirrored on the other side. Yeah, so there's a very important thing that we're doing here. That property that whatever we see on one side has to be done on the other side, just because that's just how things roll. We got the G down here with the gold chain. Anything else I'm forgetting? I think the ring would show up there. And yeah, so that's it. That's the reflexive property. So things are essentially equal to themselves. So 7 is equal to 7. A plus B is equal to A plus B. Anything is equal to itself. Pretty straightforward. All right, name a property that's illustrated by each statement. So that's it. Done with the lecture. Pretty easy stuff. Just a review of all your algebraic properties, identity properties, inverse operations, properties of equality. Yeah, let's go ahead and get started on the assignment. So look at number 1. On this one, we have x plus y is equal to y plus x. So notice what is changing from this side to this side. The only thing that's changing is we're switching the order, and we're switching the order about a plus sign. So what would we call that? So that would be the commutative property of addition, because it's about the plus sign. The next one, we have 0 is equal to 100 times 0. So if we multiply anything by 0, it goes to 0, right? This is called, I didn't actually mention this one, but it's called the 0 property, all right? Not that difficult. Then we have k plus 0 is equal to k. Now that's kind of close to the 0 property, but what's the difference? On one of them, we are multiplying. On the other one, we're adding 0. When we add 0 to anything, it stays the same. In other words, the identity stays the same. So this is the additive identity. All right, number 20, look on this one. So it's not distributing. When I see parentheses, usually the first thing I think of is distribution, but that's not what we're doing on this one. Instead, we're going from the parentheses of x plus 3 to the parentheses of 6. So all we were doing really was evaluating or simplifying the expression using PEMDAS. Please excuse my dear Aunt Sally, right? So we start out with our parentheses, and then we do exponents. There are no exponents. There's no multiplication. There's no division, at least within the parentheses first, because there is multiplication up here. And then finally, we do the addition. So 3 plus 3 is equal to 6. So all we're doing is simplifying. Then our next step after parentheses would be to multiply, right? Okay, because then we start the whole PEMDAS thing over and over again. So that's just PEMDAS, just order of operations. On the next one, we are changing the parentheses. So notice the A and the B first, and then now they want us to add the B and the C first. So we're reassociating who we're grouping with. So B used to be associated with A, and the parentheses associated with the parentheses, but now B is associated with C because the parentheses and the associations shifted. So this would be associative property. Notice all the operations here are addition. So this is going to be the associative property of addition. Also, another thing is you can abbreviate these properties if you want. So just be careful with, let me see what I can do. So like commutative, you can just do COM plus sign. You can just do 0 prop, PROP would be fine. And then, of course, our positive or additive identity. On this one, be careful with associative, how you abbreviate it. I think on the answer bank I did ASSOC dot. Of addition instead of just the 3-letter word. That would be bad because we don't use that word in my class. All right, so somebody found that out the hard way. Who was it? You know who you are. I remember who it was too, but it's okay. I forgive you. Just you didn't know better. You don't know, but you don't use that language. All right, so additive addition property of equality. So on 31, they tell us the property they want us to use. We want to complete the statement using that property. So the additive property of equality, addition property of equality means if we add something to one side, like plus 6, so if A is equal to B, A plus 6 is equal to B plus 6. We got to add 6 to the other side as well. So that is the additive identity. Or sorry, not additive identity. That would be how we would do the addition property of equality. All right, 34, multiplication property of equality. So we're going to multiply both sides by the same thing. So if we have 2/5 x is equal to 10, then we have 2x. So how do I go from 2/5 x to just 2x? What did I multiply by? Well, I'm going to end up multiplying both sides by 5, right? So if I do 5 times 5, that's going to divide to or simplify to 1. And if I multiply one side by 5, I have to multiply the other side by 5 as well. It looks like a 3. It's totally a 5. So 2x is actually going to be equal to 5 times 10, which is 50. And then now we could divide both sides by 2. Another thing, what's nice is when you're doing multiplication, you can undo multiplication with the reciprocal. So you can multiply by the reciprocal, which would multiply by 5 and divide by 2 at the same time. And that would actually kind of get you closer to the answer where x is actually equal to 25. So if you could do both multiplying and dividing at the same time, that's called multiplying by the reciprocal, which is a nice little trick. All right, 37, we're filling in the justifications for the proofs here. Each line, this is very tedious work. Technically, we would just distribute and then combine your like terms, but we can't do that necessarily without doing all the commutative and associative properties of addition and multiplication. So look at your first line to your second line. Looks like what's changing is we're going from A, B, and we have these parentheses here, so our first step is actually to distribute. So it's distributive property. And then on the next one, we have ABA, ABA. So the order is staying the same. The only thing that's changing is the grouping. We're going from the first two to the last two, and these are staying the same. So that's actually going to be associative property. And if you notice, all these are separated by multiplication. So that's associative property of multiplication. So again, that's how you abbreviate it. And then it looks like we're switching the order of B and A here to now A and B. Okay, so that's going to be the commutative property of multiplication. You can abbreviate that COM multiplication. And then we're reassociating it again, moving the parentheses from the last two back to the first two. So that's going to be associative property multiplication again. Then the last step is we're going to, I guess, simplify. I kind of left it blank because I'm not sure quite what we call that. But a times a is going to be a squared. So we're just kind of combining and condensing that down, or reducing, or whatever. I don't know what you would call it. Same thing with b, and b would be b squared. So technically there's a lot of steps going on here with associative and commutative property. You don't even normally think about using them, but we are technically using them. All right, 38. Looks like the first thing we're doing again is going to be distributive property. Yeah, so the 5 is going to be distributed to the 2 and to the c. So that's distributive property. Then the next one, oh, it looks like the terms are switching places. So this would be our commutative property, and they're switching across addition. So that would be commutative property of addition. And then, okay, so from here, that's staying the same. So on this one, what's happening is the c is being factored out. Factoring is also called reverse distribution, and it's a part of the distributive process. It's just working backwards. So it's just going to be distributive, or distribution. Then the last step, we're just evaluating it, right? So we have our parentheses first, and then we do our 3 plus 5, which is 8c, and then we can do multiplication, which will give us 10. So that's going to be PEMDAS because we're using our order of operations. All right, last problem I'm going to do with you. Good, we're under 30 minutes. All right, so on this one, the first line to the second line, it looks like we're just squaring the 3. So we're doing parentheses exponents, so that's going to be PEMDAS. Then from this line to this one, the plus negative 2 stays the same. Oh, we just subtract. So 9 minus 9 is 0. That's because it's the additive inverse. So we undo addition with subtraction. So it's additive inverse. And then when we, the 6 times 0 goes to 0. It goes away because of the 0 property. Anything times 0 is going to be 0. And then we add 0 to 2, and it goes away because 0 is the additive identity. The identity remains the same. Sorry if I'm going a little quick for you. And then same thing kind of going to happen again. 2 plus a negative 2. Negative 2 is the additive inverse of 2. They undo each other, getting us back to the identity again. So that's going to be the additive inverse as well. And then so all this, which is kind of nasty, this expression here was actually equal to absolutely nothing. And we had to use all these properties to be able to unravel it to get it where it would finally come free, which is kind of cool. All right, so that's it. We're under 27 or 28 minutes, so I hope you guys enjoyed that. We're just getting into more algebraic proofs. We're going to spend the next 2 days using these properties, so we did kind of need to review some of that algebra stuff that we did before. So when we come back Monday and Tuesday, we're going to do algebraic proofs and some geometric proofs, where we're starting to use the segment addition postulate and the so segment addition and angle addition postulate and some other basic things that we know from geometry as well. So we will do those proofs, and then we're going to move on to conditional statements, which is the main thing that this whole unit's going to be over. I don't think the conditional statements are necessarily that difficult, but you just have to catch along with the pattern. So we'll do that, and we're going to have a good week next week, and then it'll be pretty quick before, I think about 2 weeks before we take our next test. So if you're not happy with where your grade's sitting at right now, we're all starting fresh, and so just make sure you stay caught up on the homework assignments. Come to the live tutoring if you have any questions. Look at the solution manual if you can see if that can guide you through the problems as well, and make sure you know how to do it before we take our next test, because that can help bring our grades up. And make sure we're turning in all of our homework for this unit as well. That can bring your grades up as well. But overall, I think most of you guys are doing really well in my class, and I'm proud that you guys are learning so well under these conditions, and hopefully we can go back in person soon. So see you guys. Have a good day.